Alright, hello everyone. Let's look at another question on chemical equilibria. In this question we are told, consider the following reaction to be at equilibrium. In one experiment, the equilibrated system contained a certain mixture of these gases, and Kc at 900 Kelvin is 1.56. Suppose that 0.128 molar of H2 is somehow pumped out of the system. Qualitatively predict the behavior of the system, and then determine the concentration of all the species after equilibrium has been re-established. Alright, so this is a classic. There's been a disturbance to an equilibrium, and we need to figure out what's going on. Alright, so let's first talk about A. A asks, what is qualitatively predict what's going on? And what is going on is that we had a loss of product, like H2 is a product. So that means our system is going to respond to increase that product concentration again. That's Le Chatelier's principle. Or you can look at the Q, and it will also indicate to you that that is what it's going to do. So we expect our equilibrium to shift to the right for the new equilibrium to be established. That means our reactant concentrations to decrease and our product concentrations to increase. We'll also check that against our Q in B. So you can just write something like, we expect the equilibrium to shift to the right before the new equilibrium is established. Because of the loss of product, and Le Chatelier's principle predicts that the system will respond to increase the product concentration because of the loss of a certain amount of H2, which is a product. Okay, so let's look at B. Alright, so I just skipped ahead for you, don't have to watch me draw a table. So this is the table that we draw. So our old equilibrium had a certain bunch of concentration values. Then we had a disturbance. We said, suppose you pump out 0.128 molar of hydrogen. So that means we lose 0.128 molar hydrogen. Nothing else. So all of the other species do not have a disturbance associated with them. It's only hydrogen. That means the new initial concentrations for each of these species are as follows. So for the ones that didn't have a disturbance, they remain the same. And for the one that had a disturbance, it changes a bit. Alright, because it lost something. Right, so now we must determine how do these concentrations change to establish a new equilibrium. And how we do that, of course, is with the help of the reaction quotient. So we must go Q equals to concentration CO2, concentration H2, divided by concentration CO, concentration H2O. Then you put in these values. So 1.208, 0.580 divided by 0.792, 0.692. Then I got a value here of 1.278 and some numbers. And that is still less than the Kc, which is 1.56. So therefore, because Q is less than Kc, or it's not equal to K, so that means this is not an equilibrium situation, and it is less than Kc, that means that the forward reaction is favored. Alright, so that tells us information about how we must assess these changes. So that means our reactants need to decrease in concentration and our products need to increase in concentration to reach equilibrium. Alright, so that is 0.792 minus x, 0.692 minus x, 1.208 plus x, 0.708 plus x. Alright, so that's our concentrations. Our equilibrium concentrations. So now to determine x, we have to put them into Kc. Of course, we'll use Kc to calculate them. So Kc is 1.56. The Kc expression is CO2 equilibrium, H2 equilibrium, CO equilibrium, H2O equilibrium. I'm putting in those values, 1.208 plus x, 0.58 plus x, and you can technically say, sorry, I think just made a writing mistake here, 580, oopsie, I don't know why on earth I did that, 580 plus x, and at the bottom here, 0.792 minus x, 0.692 minus x. Okay, now just check that you picked up that mistake that I had for the hydrogen equilibrium concentration is now corrected. And we can't approximate. Why can't we approximate? So if you take Kc, multiply by 100, then you get 156, and that is much larger than, say, the initial concentration of any of our species, but for example 0.792, right? It's much larger. So it's not that our concentrations aren't the biggest numbers that we are working with here. It's definitely Kc. So in other words, we need to expand this and work with our quadratics. So 0.70064 plus 1.788x plus x squared. This is divided by 0.548064 minus 1.484x plus x squared. Okay, and now let's expand it to one line. I get 1.56x squared minus 2.31504x plus 0.85497984 equals to 0.70064 plus 1.788x plus x squared. Then grouping similar terms, I get to 0.56x squared minus 4.10304x plus 0.154333984 equals to 0. So let's solve that using the quadratic expression. So that means x equals to minus b plus minus the square root of b squared minus 4ac divided by 2a, and that gives me x1 equals to 0.037811 and x2 7.289 molar. Alright, now we must evaluate these values. So x2 is clearly impossible. And why is it impossible? Well, if you look at, for example, either of these that we calculate here, either concentrations at equilibrium, you would see we end up with negative concentrations. So that is why we use x1 to calculate our equilibrium concentrations. So equilibrium concentration of CO at equilibrium is equal to 0.792 minus x. X is 0.037811. So that means we get a rounded value here of 0.754 molar. The equilibrium concentration of H2O at equilibrium is equal to 0.692 minus X. So that rounds to 0.654 molar. The equilibrium concentration of CO2 is equal to 1.208 plus X, and that then rounds to 1.25 molar. And then finally, the equilibrium concentration of H2 is equal to 0.580 plus X, and it rounds to 0.618 molar. Alright, that is everything that we wanted to do. We saw that our Q agreed with our prediction of how the system is going to respond. We said there was hydrogen gas pumped out. So in other words, our system would want to respond in a manner that then produces hydrogen gas again. So in other words, the forward reaction is going to be established, or the equilibrium shifts to the right. We saw that Q predicted that. Forward reaction is favored, so a reduction in the reactant concentration, increase in the product concentrations, and then we calculated them. And there you have them. Right. So, and we again calculated the quadratic formula, used that. We used an ice table with the old equilibrium and the disturbance added as separate lines to assist us in calculating them. So, yeah, this is a very long problem, but a very useful problem as well. Good. Thank you for watching, and I'll see you in the next one.